using L'Hopital's rule. So essentially what L'Hopital's rule is again telling us we can do is we can find the limit as x approaching some value a of something that's rational. So anything that is in a rational form. So using L'Hopital's rule, we can differentiate f and g repeatedly so long as every time we continue to differentiate the numerator and denominator, we're always getting that indeterminate form 0 over 0, evaluating it at a, the number we're approaching. As soon as one, the numerator or the denominator, one or other of these derivatives is not 0 at x equals a, we have to stop. Okay, so L'Hopital's rule doesn't apply when either the numerator or the denominator has a finite non-zero limit. So let's look at some other examples, right? So in this case, this would be, we're going to find the limit for something in an indeterminate form of infinity over infinity, which behaves the same way as 0 over 0. So in this case, we're going to do the limit as x goes to infinity of e to the x over x squared. And if we try to evaluate this, which is always the first step with limits, e to the infinity over infinity squared, this turns out to look like infinity over infinity. So we'll apply L'Hopital's rule, and this is the limit as x goes to infinity. E to the x, the derivative of that is e to the x, and the derivative of x squared is 2x. So again, if I try to evaluate this at infinity, I've got e to the infinity over 2 infinity, which is again infinity over infinity. So we'll apply our indeterminate form. The limit as x goes to infinity, the derivative of e to the x is e to the x, and the derivative of 2x is 2. So now, when I try to evaluate this, I've got e to the infinity over 2, which is infinity over 2, and this is something that we can assign a value to, so my limit approaches positive infinity. Okay, so let's look at what happens when we have an indeterminate form such as 0 times infinity. So we said we need 0 over 0 or infinity over infinity, and this is not that. So we need to come up with a way to make it look rational so that we can apply that. So for our example here, we're going to look at the limit as x approaches 0 from the right of the square root of x times the natural log of x. And so we have to consider it from the right here because when you're dealing with natural log of x, the domain of that, it's not defined to the left of x equals 0. There's a vertical asymptote. All right, so rearranging this, not applying L'Hopital's rule here, this is the same as the limit as x goes to 0 from the right of the natural log of x over x, and I'm going to raise that to the 1/2 power. Moving it to the denominator makes it negative 1/2. So now, if I were to evaluate that at 0, the natural log, if we look at natural log approaching 0 from the right, that's going to go to negative infinity. And if we look at approaching 0 from the right of x to the negative 1/2, we get positive infinity. So here we have infinity over infinity. I've rearranged what I've started with to put it into that indeterminate form. And so now, at this point, I can take the derivative of the numerator and the derivative of the denominator applying L'Hopital's rule, which I've got the limit as x goes to 0 from the right. The derivative of ln x is 1 over x. And the derivative of x to the negative 1/2 is negative 1/2 x to the negative 3/2. So now this is a real clunky, ugly expression we have that I've circled right here. But with some basic algebra, we can clean that up. So this is equal to, and I'm not applying L'Hopital's rule. When I simplify that, I get negative 2x to the 1/2. Okay, so if I look at evaluating negative 2x to the 1/2 as x is equal to 0, just on the right of 0, my output value is 0. And then, thinking about what that graph right here that we have looks like, that's the square root of x graph reflected across the x-axis. So normally square root of x looks like that. But we are reflecting across the x-axis and stretching it vertically. So this is my graph. And as we consider approaching 0 from the right, my y value goes to 0 there. So this is my answer. So let's look at one more example in this video. So we will find the limit of something when we have infinity minus infinity. And you're going, well, that should equal 0, but we don't know how big the infinity is. So in this example, we are going to do the limit as x goes to 0 of 1 over sine x minus 1 over x. So in this case, considering this and how we can use L'Hopital's rule, if I tried to evaluate at 0, 1 over the sine of 0 minus 1 over 0, well, that might look like 1 over 0 minus 1 over 0. You're going, well, Ms. Stein, you can't divide 1 by 0. But think about 0 as being a really, really, really small number. So think about approaching 0 from the left or the right side, like 0.000001. When you take 1 and divide it by something really, really, really small, it becomes infinitely large. Okay, so this is why we have infinity minus infinity in this situation. So how are we going to handle this infinity minus infinity situation? Well, I want to write this as one fraction. I can get common denominators and add these fractions together. So the limit as x goes to 0, that would be x minus sine x over x times sine x. Okay, so now when I try to plug 0 in here, if I go to plug this 0 in, I would get 0 minus the sine of 0 over 0 times the sine of 0. And that should be a 0, not a theta there. So 0 minus sine of 0 is 0 over 0 times, it doesn't matter what sine of theta is, we've got 0 over 0. So now we apply our L'Hopital's rule. So we've got the limit as x goes to 0. The derivative of x is 1. The derivative of sine is cosine. And in the denominator, when I go to calculate my derivative, I need to use the product rule. Okay, so remembering if we've got first, second, and we are taking the derivative, that'd be first, second prime plus second, first prime, right? So this derivative would be x, the derivative of sine is cosine x, plus sine x, and the derivative of x is 1. So there's a little invisible 1 there. We don't need to write that. All right, so if I were to plug in 0 now, let's take that 0 and plug it in for my x's. I get 1 minus cosine of 0 is 1. So I've got 1 minus cosine 0, which is 1. So that gives me a 0 in the numerator. And I've got 0 times cosine of 0. Again, that's 1, but times 0 is 0, plus sine of 0, which is 0. So apply L'Hopital's again. And we've got the limit as x goes to 0, the derivative of 1 goes away. The derivative of cosine is negative sine, so I end up with a positive sine in my numerator. I have to use my product rule here again. So the derivative of x, let's see, we got first is x, I'm sorry, the derivative of cosine is negative sine x plus cosine x times the derivative of x is a 1 times 1, we don't need that there, plus the derivative of sine x, which is cosine x. So let's just take this, not applying L'Hopital's, I'm just going to clean it up. The limit as x goes to 0, I've got sine of x in my numerator, and I have negative x sine x, and then I have plus 2 cosine x. So now let's look at what happens if I plug 0 in for these values. I end up with sine of 0 over negative 0 sine of 0 plus 2 cosine of 0. And sine of 0 is 0. 0 sine 0 is 0, but I end up with a plus 2. Cosine of 0 is 1, so I've got plus 2, which gives me 0 over 2, which in this case 0 over 2 is equal to 0. And we're done. And you should be able to verify any of these limits we just did by, typing the original function into your graphing calculator and look at what happens as you approach the indicated or requested value.